So thank you to everyone joining us today for our first invited plenary lecture for the SIAM MPE20 series. It's a great pleasure to introduce Hannah Christensen as today's plenary speaker. She earned her undergraduate degree from the University of Cambridge and received her PhD in atmospheric physics from the University of Oxford in 2014 for her thesis entitled Stochastic Parametrization and Model Uncertainties. She has worked at the National Center for Atmospheric Research in Boulder, Colorado, and at Oxford in close conjunction with the ECMWF as a Natural Environment Research Council Independent Research Fellow in the Atmospheric, Oceanic, and Planetary Physics Department. Currently, Hannah is an associate professor in physical climate science at University of Oxford within the physics department. In the great tradition of Ed Lorenz, Hannah has in her career expanded our knowledge on how to parameterize unresolved processes by synergistically vacillating between simple toy models and large-scale operational numerical weather forecasting models, moving from Lorenz models to general circulation models with great ease. Hannah's work has made major contributions to highlight why we should and how we can best account for inherent model uncertainty as well as parameterize unresolved physical processes. In particular, she examines those processes which are either too fast or too small, or both, to be captured by numerical models but still carry important dynamic information, doing so in a stochastic way rather than using the historical deterministic approach. Hannah has made significant contributions to our understanding of how to best implement the widely used method of stochastically perturbed parametrization tendencies, which are commonly used by operational weather forecasting centers. Hannah's work has underscored the importance of multiplicative noise and the importance of judicially choosing temporal and spatial correlations for stochastic parametrizations. Her work has wide-ranging applications, including for numerical analysis of ENSO, the parameterization of atmospheric convection, the Asian summer monsoon season, among others. And beyond this, Hannah has also been actively involved in outreach to industry and the general public at large, working to advance and broaden the understanding of numerical weather prediction. Today, Hannah will describe to us the challenge of developing stochastic parameterization schemes that skillfully mimic unresolved small-scale processes and the potential of very high resolution simulations to indicate the form that stochastic schemes should take. Several climate model experiments will be depicted as a demonstration of the potential for improving climate simulations using stochastic approaches. So we look forward to Hannah's presentation today. I ask that all the participants, as you have questions during her talk, to go ahead and utilize the chat feature. And when she concludes, then we'll go through the questions at that time. So thank you so much for joining us, Hannah, and please feel free to proceed.
Well, thank you for your introduction, Jessica. Hello, everyone. So yes, today I'm going to give a very kind of general overview talk about the stochastic parametrization and its use in weather and climate models. I'm going to give a bit of an introduction, and then, as Jessica said, I'm going to spend some time talking about how we can use high resolution model simulations as a way to characterize errors in lower resolution models and thereby design stochastic parametrizations that we can use in those low resolution models. And then I'm going to round off the talk by talking about some new results looking at stochastic parametrizations that were really developed for the weather forecasting community, and talking about how taking those schemes and putting them in climate models. I'll thank my collaborators who've put a lot of work into this as well, and I get started. Ooh. So I'm going to start off by just putting up my take-home message, and I have 2 points I'd like you to take home. So firstly, that stochastic parametrization is a physically justified approach to developing forecast models. And secondly, that stochastic parametrizations are beneficial for simulations on a huge range of timescales, ranging from short range weather forecasts all the way through to decadal-long climate predictions. So what is the problem we have at hand? So we would like to make forecasts of the beautifully complex Earth system here on the left. And the tool that we have to do this are computer simulators or computer models of the Earth system. So I'm particularly going to focus on atmospheric models in this talk, but really my comments apply to other components as well. So what we do is we take the equations of motion that describe the atmosphere, and we discretize these equations onto some grid. But of course, we know that there are going to be processes occurring at scales smaller than this grid box scale, which we have to represent in some way, particularly the impact that these small scale processes have back on the resolved scales. And so the solution to this problem then is to design parametrization schemes. I mean, the process of designing these parametrization schemes again introduces various problems. So in particular, we have to make various approximations and simplifications when designing these schemes. Perhaps the most fundamental simplification that we make is captured in this paragraph that I've taken from a very famous parametrization paper, this paper by Arakaya and Schubert. So let's read their comments. It says, consider a horizontal area at some level between cloud base and the highest cloud top. This horizontal area, which we designate as our unit horizontal area, so that's equivalent to our grid box then, is shown schematically in this figure. It must be large enough to contain an ensemble of cumulus clouds, but small enough to cover only a fraction of a large-scale disturbance. The existence of such an area is one of the basic assumptions of this paper. So what this paragraph is saying then, this extract, is that they are assuming that there is a scale separation that exists in the atmosphere. And so there must be a scale separation because we can find some length scale, some grid box, which is a lot larger than the process we're interested in. So in this case, cumulus clouds. But at the same time, it's a lot smaller than the large scale kind of variability in the system. And so what this means then is that within our grid box, there's a large number of cumulus clouds, and that all of the clouds are experiencing the same large scale environment because the large scale state hasn't varied. And so this means that they're statistically indistinguishable from each other. We can meaningfully average over this large ensemble of clouds and thereby come up with some deterministic mapping that tells us what the effect of these small scale clouds is going to be back on the large scale state. But the problem is that we don't observe a scale separation in the atmosphere. So here's a figure taken from another famous paper. So this is the spectral density as a function of wavelength from Nystrom and Gage. And so what we can see is that there is a continuum of scales of motion in the atmosphere. So we can't find a length scale at which there is little power, which we could put our grid box. And so we need to find such a length scale in order for those assumptions in the earlier paper to be true. And this follows our experience of the atmosphere. So I mean, here's a satellite image over New Zealand. We can see that we might be able to find a grid box somewhere up here in the top right of the picture where we've got many clouds, but that's certainly not the case at all places in this image. So, so in general, this idea of scale separation is not going to be valid. So we've said that then we don't observe a clear separation of scales for many processes. And so what this means then is that our grid scale variables are not able to fully constrain the subgrid scale motion. So in general, we can't come up with a deterministic mapping that tells us what the subgrid scale processes are doing and how that feeds back onto the large scale for a given large scale initial condition. And so this is then where stochastic parametrization comes in. So instead of going through this deterministic framework, we can develop a stochastic scheme which describes the subgrid motion as some probability distribution that is constrained by the resolved scale flow. So instead of the previous paradigm, where at every time step we're predicting the most likely, our kind of best guess for the impact of the subgrid scales, and using that to step us forward in time. We're now in the stochastic framework, where at each time step we're drawing from this probability distribution to give us one potential realization of the subgrid flow. So then we get a different realization at each time step, and then these different realizations can feed back into the evolution of the model. Okay, so I'm going to now take a slightly different tack. So we've seen then why stochastic parametrization could be justified from these kind of physical arguments. But let's look at a slightly more practical reason. And so to do so, I'm going to talk a little bit about ensemble forecasting. So ensemble forecasting is routinely used to make probabilistic weather and seasonal forecasts. So the idea is that instead of making a single best guess prediction for the future weather, you make many forecasts using your model, and you consider that each of these forecasts are equally likely, and that then they can indicate the distribution of possible future weather, thereby indicating what the uncertainty is in the forecast. Now, there's been a bit of pushback from the public when we move to making these probabilistic forecasts. And I think the reason is that it seems too much like we're hedging our bets. You know, if you say a 10% chance of rain on Saturday, then effectively you can never be proved wrong, because if it does rain, you can say, oh, well, I did say 10% chance of rain. But actually we can show that these kind of probabilistic forecasts are extremely useful. So what we can show is that, we're really able to produce forecasts which are what we call reliable. So these reliable forecasts have the property that the observation, what actually happens, behaves as if it was drawn from the forecast that we predicted. And these kind of forecasts are then very useful. And the other quality of a forecast that we look for is called resolution. So this is the property that a forecast, and kind of the distribution of the forecast, changes from case to case. So a good example of this is this set of 3 hurricane forecasts from the ECMWF system. And you can see they're all very different. This is showing plumes of the eye of the storm. We can see that for Sandy, for example, the system was extremely confident that it was going to take this very unusual track and turn left and strike New York. But whereas for these other 2 hurricanes, so for Katrina and then for this other hurricane Nadine, there was much more uncertainty in the track that the hurricane would take. And there's useful information here for decision makers. Really the key to making a probabilistic forecast like this, which has this property that it's reliable, is that we have to capture all sources of uncertainty in the forecast. And on these kind of weather and seasonal timescales, there are 2 main sources of uncertainty that we need to account for. So the first is one which is, of course, familiar to anyone who's read Lorentz, which is then initial condition uncertainty. So we know that the atmosphere is a chaotic system. We know that there are bound to be errors in our starting conditions for our forecast, and that over time, these errors will then grow and infect the large-scale state in our system. The solution to this then is that when we make our ensemble with many forecasts, we take the starting conditions and perturb them slightly between different ensemble members. And there are various ways of generating these perturbations, for example, using information that comes out of the data assimilation system. So we can then capture that uncertainty and see how it propagates into the future. And of course, the other source of uncertainty, the one which I'm particularly interested in, is this model uncertainty. So as I've alluded to, when we develop our forecasting models, we make many simplifications and approximations, and necessarily then these introduce errors into the forecast again. And so this is where stochastic parametrizations can come in as being really useful as a way of representing this uncertainty. Instead of always predicting the most likely cloud, impact of clouds on your forecast, for example, the most likely subgrid state, we can draw from the possible range of realizations. And then because of the nonlinearities in the atmosphere, these will then pan out into really quite different evolutions of the model. And it's for this reason that stochastic parametrizations were really developed by originally the weather forecasting communities. They could see that their forecast models where their forecasts were missing some source of uncertainty, because too often the observations fell outside of their ensemble forecast. And so here we've got some, this is some a very early paper showing the impact of stochastic schemes in a weather forecast. So what I'm showing here is the forecasts of temperature, I think at 850 hectopascals in the tropics, out for a couple of weeks here. And on this, the y-axis here, we've got a root mean square. It's either the root mean square error in the ensemble mean for these lines with crosses, or it's the root mean square spread of the ensemble for the lines without crosses. So if our forecast model is reliable, the spread of the ensemble should be a good indicator of the expected error in the ensemble mean, and the line with crosses should lie on top of the line without crosses. So the grey line is the kind of original version of the forecasting system. So we've got initial condition perturbations, but no representation of model uncertainty. And we can see that here in the tropics, the ensemble is woefully underdispersive. It's far too tight. The observational error is too large compared to the spread of the ensemble. But putting in any of these different flavors of stochastic parametrization both improves the ensemble spread, but also improves the root mean square error. So the ensemble mean is actually then a more accurate predictor of the observations than it was without the stochastic physics. So this is, again, the nonlinearities of the atmosphere coming into play. And because of these big benefits, stochastic parametrization is, ubiquitous in the weather and seasonal forecasting community. So the next question then is, okay, so we clearly need stochastic parametrizations, but how can we go about designing stochastic parametrizations? So, what I'm showing here is a very general framework for how we can go about this process. So we start off by identifying some uncertain process in our forecast model. So this could be a very specific process. So for example, how convection is triggered, for example, or it could be a much more kind of general process. So for example, it could be taking all of the physics, all of the parametrization schemes in our model and looking at uncertainty in those. But having identified some process in our model, we then want to characterize the uncertainty in that process. And this can either be through kind of theoretical ideas and combined with measurements, so perhaps from observations or from model data. And then having characterized the uncertainty, you're essentially there with your stochastic parametrization. You implement this kind of approach in your model where you're using stochasticity, random numbers, to draw from this distribution that you've characterized above. So I'm now going to spend a few minutes talking about how we can really make use of measurements as a way of characterizing uncertainty in our forecast models, and thereby designing stochastic parametrizations and motivating improvements to existing schemes. So the approach that I'm using here is a coarse graining approach. So I start off with some high resolution model simulation, which I kind of define to be my truth. So I take this as my target that I would really like my low resolution model to be able to mimic. So the first thing I do then is I coarse grain this high resolution data set down to some forecast model resolution. And then I use a forecast model to step forward this initial condition field to some later time. I then let the high resolution model run and again coarse grain and compare these two coarse grained fields at a later time. So what I'm thinking here is that then the difference between what the forecast model said would happen and what really happened in the high resolution simulation, this difference is effectively the error in this low resolution forecast. So we can then characterize the statistics of this error to learn something about how we can build a stochastic scheme. So in particular, the experiments that I'm going to show you on the next few slides are taking an existing high resolution simulation that was produced as part of a project called Cascade. So that was by Chris Holloway and his collaborators in the University of Reading. So this particular model is the UK Met Office limited area model run at 4 kilometres. And I've got, it covers this large region here, so it's about 15,000 by 5,000 kilometers in its domain, and it spans 9 days of data. So what I first do then is coarse grain this 4 kilometer run down to 30 kilometers. And so I've chosen 30 kilometers as that's a fairly typical resolution for a global ensemble forecasting system. And then what I'm going to use as my forecast model is the European Centre's IFS, the Integrated Forecasting System. But instead of using their full model, what I'm going to use is their single column model. So effectively, a single column model is when we take the physics parametrization schemes out of a global model. So we extract this, the kind of contents of a grid box, and we can run it as a standalone model. And then what you do is you prescribe the dynamical tendencies that this subgrid scale box would see. We use that model then to step forward this field in time, and we do it by running the single column model independently for each of these pixels. And I'm going to look, I'm going to make 1 hour forecasts with my single column model, and then look 1 hour later in my high res model. And so I'm characterizing the errors in the forecast model that have developed over this kind of 1 hour forecast. I mean, so the first thing we can do is something that's very simple. So I've got a huge amount of data here. It's about kind of 65,000 grid boxes in my coarse grain domain, and I've got 9 days hourly. So what I can do is I can sort my data according to what the single column model predicted would happen, and then look at what actually happened in the cascade high resolution data set, given what the single column model predicted. As a way of characterizing the random error associated with my single column model forecast. So that's what I'm doing here. So each of these panels is showing a different predicted temperature tendency. So the change in temperature over that 1 hour window, the prediction from the single column model. And that's also highlighted as this thin gray bar in each panel. And then the blue histogram is showing the distribution of this temperature tendency that I can see in cascade that's associated with that single column model forecast. So what we can see is that there is information in the forecast in the single column model. So in general, if we're predicting a cooling tendency, we tend to see a histogram from the true distribution that's kind of moved towards cooling. And so we can see the mean of these true distributions is moving smaller as the forecast gets smaller. But it's certainly true that there's a lot of variation that we see in this kind of cascade data, which is not being indicated by the single column model. And so this spread in the histogram is telling us about the error associated with the deterministic prediction. There's some other interesting things to note. So for example, when we predict a zero heating tendency, there is actually some residual uncertainty associated with that. And that also the spread of these PDFs seems to increase as the magnitude of the predicted tendency increases in both the negative and the positive direction. So it seems that as we predict larger and larger tendencies, we're more and more uncertain in our prediction. But I mean, it's certainly true that this shows that coarse graining can give us further evidence that parametrizations could be stochastic. So to add on to the kind of physical justification that I started off with and the really pragmatic we needed in weather forecasts, ensemble weather forecasts, we can add on these this evidence from coarse graining studies. But we can go further with our coarse graining studies because, I mean, what we can do then is start measuring the statistics of this error, both the random and the systematic error, between our forecast model and the kind of true evolution of this high resolution model, and use this as a way to improve our stochastic parametrization schemes. So as a case study of how we can use these kind of coarse graining approaches, I'm going to consider this very simple stochastic parametrization called SPPT, the stochastically perturbed parametrization tendencies scheme. So this scheme is designed to represent random errors in our forecast due to all of the model's physical parametrization schemes. So it's not targeting a specific process like convective triggering, as I mentioned, but it's really capturing the uncertainty due to the entire parametrization process. But a good reason to consider this scheme in particular is because it's a very popular scheme. It's probably the most widely used stochastic parametrization. It's used in a very large number of operational forecasting models, both for weather and seasonal forecasts. And it has also been implemented into a number of climate models, including one that's being used in the kind of current CMIP, an IPCC report. So what is the scheme? Well, in a kind of normal deterministic model, the total tendency or change in a variable from one time step to the next is given by a part that's coming from the dynamics in the model. So that's solving the Navier-Stokes equations on the coarse grid, and a part that's coming from the subgrid physics. So what SPPT says is, well, the physics part is uncertain because we've made lots of approximations there. So we're going to represent that uncertainty by multiplying the physics tendencies by a random number. And so E is representing a random number. It's a spatial field. It's correlated in space. This is a snapshot of the kind of field that we might use. And it's also correlated in time, but with a mean 0. So we've got a 1 plus E here, so that we, in general, are not enhancing or suppressing the physics. So that would just happen locally and for a few time steps. Yes, so there's various other kind of assumptions made in this SPPT scheme. So you can see that all of the parametrizations are seeing the same random perturbation. It's also constant in height. So this is just a 2D field, whereas we're perturbing the whole column with the same number. And all variables see the same perturbation. So whether it's temperature, wind, humidity, they all see the same perturbation. So I should say that in those histograms, which we were looking at a moment ago, we noticed this property that as we went to larger and larger tendencies, the standard deviation of the histogram got larger. The standard deviation of the kind of true tendency got larger. So actually this property is what is captured by SPPT in using this multiplicative noise approach. So we've actually already seen some evidence for why SPPT is such a successful model. It seems like to first order, multiplicative noise is a good representation of the uncertainty in the tendencies. So can we go further and characterize some of the statistics of what this E term should look like? So what we can do is we can start off by taking our SPPT equation and identifying some of the terms in it. So T, the total tendency, we're going to take from the Cascade dataset. So this is our target, which we would like to make our single column model tendencies mimic. The D, the dynamics term, it kind of comes from the single column model, but ultimately it's being fed in from Cascade, and we're assuming that's correct. And P is our physics parametrization tendency, and this is coming from the single column model. So what we then want to do is find, for every time step and every spatial location, what the optimal E is to map these two terms onto this tendency term here, this total tendency term. So this is very simply a rearranging of this equation. It's very over constrained. We've got, of course, got vectors of the different physics tendencies in height for each of these different variables, and we're just wanting to find one single multiplicative perturbation that is valid for all of the variables at all heights. So we solve this in a minimizing the squared residual type way. And what we end up with then is a map, snapshots of what this optimal multiplicative perturbation should look like. So this is just one such image. So I've got these every hour for the whole data set. And this then is directly comparable to this image I put up earlier, which is showing some of the statistic, kind of a snapshot of the pattern that's used in operational models. And so you can see that there are some kind of large-scale spatial correlations present in this data, but there are also much smaller scales present, which we certainly are not including in our forecast model. A few more comments about the statistics of this field. I mean, the operational mean that we tend to use, so this is in the ECMWF model, is have a mean of 0. We've got a mean very close to 0 in our perturbation here, so that's good. The standard deviation that we tend to use is 0.55. So it's worth emphasizing that these stochastic parametrizations are a very large kick to the model. We're really substantially increasing or reducing the tendencies at a given time step. But interestingly, the standard deviation that we measure from this field here is also at the same order of magnitude. So it's a little lower, but it's at 0.4. It's actually also quite large. So we are seeing that it's necessary to have these quite large adjustments. So while normally we're using a Gaussian perturbation, we find that for these perturbations, we're measuring a positive skewness. So this could also act to kind of further almost compensate for the fact that then we have a smaller standard deviation here. So we saw that the spatial correlations in particular seem to be smaller just from that map. We can go further and quantify this. So here in the black crosses, I've got the autocorrelation function in latitude, longitude, and time. And then in yellow is a function that I've fitted to it to capture this decorrelation. And compare that to the blue line. So the blue line for each of these panels is what's used operationally ECMWF. So you can see that in space, they're imposing a much larger correlation scale than we actually see. But in time, interestingly enough, it's fairly similar. And in fact, while initially we have a faster drop off in the measurements, then we have this very long large correlations at quite long lags, which is not in their model. So having then made these measurements, we can go ahead and implement this into the ECMWF forecasting model, and that's actually something that we're testing at the moment to see what kind of impact that has. So really that was just a kind of a first glimpse at how we can use this data to go ahead and in this case, improve existing parametrizations, for example, by constraining the parameters in them. But you can also use the data more generally. And so we've also used it to motivate new forms that a stochastic parametrization can take. But perhaps check out this paper that's come out this year if you want to see a bit more how we use the data in that way. Okay, we'll come back to my take-home messages slide. So thus far, I hope I've motivated to you that stochastic parametrization is a physically justified approach to developing forecast models. So we've seen, we've seen arguments from the lack of scale separation in the atmosphere. We've seen kind of pragmatic arguments about how it really does improve our ensemble weather forecasts. But we've also seen that high-resolution simulations can provide more evidence about the presence of this kind of missing variability in our deterministic models, and can also be used to then characterize this missing stochasticity. So this then brings me on to my second take-home message, where I'd really like to stress that stochastic parametrization is beneficial for simulations on these longer timescales, so in climate models. So why might this be the case? Stochastic parametrization was initially really proposed as a way to improve our ensemble weather forecasts. Well, we can think of stochastic parametrization as being a way to improve the variability of weather in our forecast model. And in improving the variability of weather, we should also improve the statistics of the climate in our model. So, this is an old idea. So, for example, this is a quote from Hasselmann's famous paper. Slow changes of climate are explained as the integral response to continuous random excitation by short period weather disturbances. And we can come up with various different mechanisms by which this could take place. So this could be noise-induced drift, noise-enhanced variability, or noise-activated regime transitions. And so that last point is illustrated by this figure here of a ball in a double potential. And so with some added stochasticity, you can help this system explore this secondary regime. And really, so what we've done is we've been testing these stochastic parametrizations from the weather forecasting community, as well as developing new ones, and testing them in climate models. And we're finding some really very exciting results. And this is in a huge range of different processes. So from very basic, kind of very fundamental properties of the model, like the mean, annual mean precipitation field, we find that, for example, here in the control version, this is the EC-Earth model. We have too little precipitation here in this tropical band. So this is the difference between the control model and our observations here, era 40. And on putting the stochastic parametrization in, you see an enhancement of the amount of precipitation in these regions. So we're really compensating for this bias. We also see improvements in a wide range of different processes and modes of variability. So this is some new results looking at the impact of stochastic parametrizations on the MJO, the Madden-Julian oscillation. Madden-Julian oscillation is the dominant mode of variability on intraseasonal timescales. So it's a kind of propagating, coupled dynamics moisture mode that encircles the Earth around the tropics in a kind of 30 to 60 day time scale. We see that the phase speed of this mode in observations is fast. So this is in the kind of the space of the leading EOFs of the mode, but it's 7.5 degrees a day. And all these models that we've looked at are much too slow. So here we've got 4 different low resolution runs and 3 high resolution runs. We don't see much improvement, but a low resolution stochastic run, we are seeing a significant systematic improvement in this metric. This figure here is from a paper by Pierluigi Vidale and co-authors, recently submitted, looking at the impact of stochasticity on tropical cyclone counts. Here we're going from a low resolution model to a low resolution stochastic model. We see an enhancement in the number of tropical cyclones, very similar to what we see if we go to a higher resolution model. And then here on the right, we've got some new work coming from Christensen, who spoke earlier in the stochastics group. So if you missed that talk, do check it out. And he's showing that putting in stochasticity, this time in the ocean model, improves the teleconnection between Kara sea ice levels. So the Kara region is just off the coast of Siberia. So between Kara sea ice and the NAO. So actually the amount of sea ice in this Kara region is a source of predictability for the NAO, which is otherwise missing in the control version of the model, but we see in observations, and we see it appearing in the stochastic version of the model. So you can see this is a huge range of different processes. And I mean, for each of these results, then we need to go into the model and try and understand how the stochasticity is interacting with the existing kind of representation of the phenomenon in the model, and really then trying to unpick the mechanisms. So instead of just giving you a list of results that we're seeing, I wanted to take some time in explaining how stochasticity impacts one particular phenomenon. And so what we're going to look at for the rest of the talk then is ENSO. So ENSO is the El Niño-Southern oscillation. I'll explain it a bit more in a minute. But before then, I just thought I'd show you the impact that stochasticity has on this mode. So here we've got the power spectrum of this mode of variability, ENSO. In observation. So you can see that ENSO has a period of between about kind of 2 and 7 years. It's a very broad power spectrum, so it's got a lot of variability. Here we've got a control version of our model. And you can see here that ENSO in this model is too periodic. So we've got these 2 big peaks at kind of 3 and 4 years. And there's also too much power in ENSO. So it's got too large an amplitude. And if we move to the stochastic version of the model, we see that those big peaks have been pulled down. So the amplitude of ENSO is improved, the amount of power in the oscillation has improved. And we've spread the power out to a much wider range of frequencies. So we're seeing a much more irregular oscillation, which is much more similar to what we see in observations. How can we understand this? And I should note that, I mean, the time scale of the noise that we're putting into this model is 6 hours. So don't think that we're just jiggling ENSO, which is why it's got more variability. I mean, the time scale of ENSO is vastly different at 2 to 7 years. So there's very interesting processes going on here. But firstly, what is ENSO? So ENSO is the El Niño-Southern Oscillation. It's a coupled ocean-atmosphere phenomenon in the tropical Pacific. So in the normal conditions of the tropical Pacific, we have warmer waters over here in the west, and over the warm waters we have a lot of convection. The convection drives an overturning circulation, the Walker cell, and the return branch of the Walker cell interacts with the ocean to then maintain the tilt of the thermocline, which is the boundary between the mixed part of the mixed layer in the ocean and the deep abyss. So the returning branch of the Walker cell maintains this tilt, which keeps the warmer waters over here in the west, thereby kind of keeping the system in this state. In an El Niño condition, what happens is that the warmer waters move a little bit further to the east, and the convection follows the warmer waters. This then weakens the overturning circulation, weakening the thermocline tilt, allowing the warmer waters to move further east, etc. So we've got this coupled feedback loop. We also have a cold condition called La Niña, which is the opposite, when convection moves much further over to the west. And I mean, one of the reasons this is a very interesting and important phenomenon to study is because it impacts extreme weather events worldwide. So the presence of an El Niño or a La Niña event essentially can determine whether you have drought or flooding events, the number of hurricanes you have in the kind of Pacific and Atlantic basins, and many other things. So we need to capture this in our models in order to capture these extreme events. I mean, the processes I described on that slide are really describing a very regular ENSO, you know, this very regular coupling. But actually, we find that variability in the atmosphere is a key source of irregularity in ENSO. So a particular phenomenon has been highlighted called westerly wind bursts. So these are very strong westerly or eastward wind events, which tend to be associated with different physical processes like tropical cyclones or this magnitudian oscillation. And the presence of these strong eastward westerly wind events can then lead to a strong El Niño event developing. So it's possible then that, I mean, putting stochasticity into our model is improving the variability of the atmosphere in that model, and thereby interacting with ENSO in this way. So we can start to see how stochasticity might be having such a big improvement. But first, back to our results. So I'll say a little bit more about what I've actually done here. So the model that we're using is the CCSM4 model, the Community Climate System Model 4 from NCAR. It's a 1 degree run. We've got a nice long simulation. And the stochastic parametrization that we're using is the aforementioned SPPT multiplicative approach. So firstly, what impact does this have on the mean state? Well, it actually has a fairly modest impact. So here we're looking at the average sea surface temperatures in the control run minus those observed, and we can see we've got some fairly large biases of up to kind of 3 degrees in the Pacific Basin. And the stochastic scheme does slightly improve these biases. So here we've got stochastic minus control. If the colors are opposite to the top panel, then we're seeing an improvement. But I mean, if you look at the color bar here, I mean, the amplitude of this improvement is kind of 0.2 of a degree. So it's very small compared to what this original bias was. So not very large improvement in the mean state. However, we're seeing a very large improvement in variability in the model. So this now is the annually averaged sea surface temperature variance, the difference between the control and observed, and then again the impact of the stochastic scheme. And so here we're seeing a very good correction in terms of this bias. So we're now seeing a very good a match between the stochastic model and the observed variance. So how can we understand these results? What I'd like to talk briefly about is how we can use a much simpler model, a simple dynamical system, to motivate some hypotheses, which we can then test in our climate models. This is very much in the spirit of our prize lecture that we heard earlier in the week. So here's the simple dynamical system that I'm using. This is a stochastic delayed oscillator model of ENSO. So H is the only variable that we have here, and this is the Eastern thermocline depth anomaly. So what we have is that the change of the thermocline depth is dependent on both a Kelvin wave and a Rossby wave. So the Kelvin wave travels to the eastern boundary, excited by atmospheric terms. The Rossby wave first travels west and then east, so this has a longer time lag. And then there's also a dependency on the annual cycle. So where the atmosphere comes in is here in these A terms. This represents the positive feedback, whereby the thermocline depth anomaly leads to a change in the wind, which then triggers these different Kelvin and Rossby waves and then feeds back on the thermocline. And hidden in this A is a coupling strength parameter kappa. And so this A of H function looks like this. This is all described in these two early papers here. And what we find is that in the deterministic version of the system, if you have a strong enough coupling strength, the system undergoes a Hopf bifurcation and you see spontaneous oscillations emerging. So what I've done is that I've gone in and I've changed this coupling parameter to make it stochastic. So here I'm representing the impact of atmospheric noise in the system. So sometimes we have these kind of stochastic westerly wind bursts and sometimes we don't. And the form of my noise is a multiplicative term. So again, in the spirit of this SPPT multiplicative scheme. And what we find is that the impact of the multiplicative noise is to reduce the amplitude of ENSO. So this is exactly what we saw in the CCSM model, is that we put noise into the system and the amplitude of ENSO reduces. So here I'm showing just a little snippet from the bifurcation diagram, just to the right of the bifurcation. And the different colored lines are different amplitudes of noise. And you can see that as the noise gets stronger, the amplitude of the oscillation weakens. So this motivates two hypotheses. So the first is that maybe our stochastic scheme just simply alters the coupling between the atmosphere and ocean. So we're just moving up and down this diagram in the kind of left-right direction, thereby reducing the amplitude of ENSO. Or the second hypothesis is that we're directly impacting variability in a component of ENSO. And so, for example, through westerly wind bursts, and then this alters the shape of the bifurcation. So then we're moving kind of up and down in this way to different colored curves. So to test this, we can return to our model and analyze some of our variables to assess whether we're changing the coupling in the model. And so to really do this, I'm introducing a new set of simulations here. These are atmospheric only simulations I'm showing on the left. So here we prescribe the sea surface temperatures and then let the atmosphere evolve. But here then we've cut the coupling loop here between winds and the sea. Because obviously a change in the wind cannot affect this prescribed sea surface temperature field. So let's look at the impact of SPPT on precipitation variability. In the AMIP runs, we see no real systematic impact, though in the coupled runs, we do see this very systematic reduction. But I mean, what this tells us then is that this SPPT scheme is not directly affecting convection in any way. So this is really just following what the underlying sea surface temperatures are doing. We have to improve the sea surface temperatures first in order to change convection. However, if we look now at the variance of the wind in the uncoupled and coupled runs, we see a much more similar picture. So there's a bias in the variance of wind in the control run, in the AMIP, control AMIP atmosphere only run. And putting in this SPPT scheme reduces this bias, so it damps the variance in the wind. So it seems that first what we're doing with this stochastic scheme is doing something to do with the winds. And there are two different processes which set the wind in the tropical Pacific. The first is coming through from convection. So heating from convection leads to upper level forcing, which affects the winds. But we know that we haven't changed convection by SPPT, so we can rule that one out. And the second process is through SST gradients affecting the boundary layer, which again affects the zonal surface wind. So it seems that this is the path which we must be affecting. And so this really is a change in the coupling between how SST affects the atmosphere. So it seems like putting in our stochasticity does impact the coupling in this way. I think I'll probably skip over this slide in the interest of time, but I mean, we've also looked then at the impact on more direct modes, kind of high frequency variability in the model, such as westerly wind bursts, where we see a kind of modest impact. We have also tested stochastic schemes in a second climate model. So this is the EC-Earth model, run at a very similar resolution, also coupled. And in this model, we find that the control version of the model has too weak an ENSO. And extraordinarily, if we put in the same stochastic parametrization, we see an enhancement of ENSO in the model. So here again, we're looking at the power spectra. We can see that the power spectra for the control model is too damped. There isn't enough power in ENSO. But putting in the stochastic parametrization has really enhanced the amount of power present in ENSO. And so can we use our delayed oscillator model to explain this difference? So now I'm showing you the rest of the picture here, the rest of the bifurcation. So while above the bifurcation point, we saw increasing the amplitude of noise in our system damps the oscillation. Below the bifurcation point, if you have a little bit of noise, you can still have an oscillation. And then as you increase the amplitude of the noise, you can enhance the oscillation. So perhaps we can think that EC-Earth in general is sitting below this bifurcation point in terms of ENSO. It has some kind of oscillation because of the more kind of random behavior of the atmosphere in the model, but putting in stochasticity enhances this oscillation. Whereas CESM has a self-sustaining ENSO, and putting in some variability into the atmosphere, extra variability from a stochastic parametrization then damps it. The question, of course, is where the real world sits, which I don't think we know. So this then brings me really to my conclusion slide. What next? So it's clear that we need to continue to develop improved schemes for both weather and climate models. I mean, while our weather forecasts are pretty reliable, there is definitely room for improvement. And of course, our climate models, we're seeing these big improvements when we use stochastic schemes. So I really want to advocate this idea of combining theoretical ideas with measurements, including those from high resolution models. But I also think there's potential for new approaches, potentially using machine learning, and there have been a few papers in this direction that have come out recently. Secondly, of course, I've talked a bit about this very exciting new area of looking at stochastic parametrizations in climate models. And we're seeing a lot of positive impacts emerging, but really these need to be understood better. Though it does seem like perhaps we can use stochastic schemes as a way to complement other ways of representing uncertainty in climate simulations, such as perturbed parameter simulations or the kind of CMIP style multi-model ensembles. But we do have issues when we start trying to do this. So one of the big problems that we've come across is that taking these schemes from weather forecasting centers and just putting them in is sometimes not ideal because the approaches are not conservative. So we need to make some improvements here. And we also need to address uncertainty in all the different components of the Earth system. So again, Christian talked about this earlier in the stochastic session. And then finally, in order to understand how stochastic parametrizations have the impact they do, we really need to just improve our understanding of the underlying physical processes going on. So for example, for ENSO, we saw that putting in variability on the 6-hourly time scale had an impact on this, this mode of variability with 4 to 7 years, and potentially impacted different models differently because of the way that they were formulated differently in terms of this kind of coupling or effective coupling between atmosphere and ocean. So I think there's a lot of room for more progress that we need to make here in terms of understanding. And so then I'll leave up my take-home messages, and thank you all for listening.
Thank you so much, Hannah. And this is the moment where if we were all sitting in a room together, everyone would be applauding. So a few questions have come through on the chat. So I'll just go ahead and read them for you to respond to. So we have the first question from Itamar Halavi. Can SPPT be viewed as a statistical trick to cancel errors that are due to subgrid processes?
So can SPPTs be used as a statistical trick to cancel errors due to subgrid processes? I'm not sure I would view it as a trick, because I think it's being very kind of honest in what it's trying to do, which is recognizing that these subgrid processes, have errors associated with them, because it's not possible to make a deterministic prediction because of, as I talked about the lack of scale separation. So I suppose it's not really cancelling errors, but it's more trying to capture the errors. So I think, I should say that I also think there is room for improvement in our deterministic parametrization schemes. So, for example, some of the error that is mopped up by SPPT is going to be a kind of systematic error, which could be improved. So maybe there's a missing process in our model, which is, which we could build in, and then that would improve the model for those cases. So I think that at the moment SPPT does a bit of that as well, but I think there is underlying random error which we wouldn't be able to correct by just making improvements to our deterministic schemes.
Okay, thank you. So we have another question from Christian Stroman. He asks, he's curious about the large spatial autocorrelation in the SPPT scheme versus the very low spatial autocorrelation estimated in your experiments. And he wonders, might this justify implementing stochastic perturbations that are strongly local in nature, even fitting the noise statistics at each grid point separately?
Oh, thank you, Christian. So, so it's I think that is one of the most marked differences between the kind of coarse graining work and what's usually done in models, is this difference in the spatial scales. So I should say that the original schemes in the kind of operational models, the scales were come up with in a fairly ad hoc way. So they were chosen as being scales that they thought were reasonable, and then tuned to make sure that the models gave a good spread to error ratio. And so that's why they're there, and they're so large. And in particular, the larger scales were found to be important on seasonal time scales. So there is some scope that if I had a larger domain and a longer data set for my coarse graining, that I would find some larger scales emerging. But otherwise, it's true that I find a big component of this kind of grid scale noise in my forecasts, in my experiments. But yeah, so I don't know what to conclude from that, really. I think, I think it is still important to have these larger scale correlations. So I don't think we should just do local estimates of the statistics, but perhaps, but perhaps we're overdoing it a bit with the scales that we're currently putting in, or perhaps we need to make some improvements to more the kind of deterministic part of the model, which might be then, correlated over a large spatial scale. If that answers the question.
Okay, and I think we have one more question I'd like to pose to you in the interest of time, because I know there's another session that is forthcoming after this, also on stochastic models. So this is from Marcus, and he asks, do you also think it's appropriate to use stochastic parametrization to address uncertainties that are fundamentally epistemic rather than aleatory? Is the necessary assumption that aleatory uncertainties dominate over epistemic?
I think I might have to ask you to clarify. Can you give an example of?
So Marcus, this is his question. Let's see if we can unmute him and so he can speak. Or can you unmute yourself? me see if I can, there, I think you should be able to talk now.
Hi, very nice talk, Hannah. So I'm just wondering about things like land surface processes, things, or cloud microphysics, things where we fundamentally don't know big chunks of the processes, where we might have whole processes just missing from our models. Is that something that's appropriate to address via stochastics? I think you answered this a little bit in your conclusion bullet points.
Yeah, so I think that processes that are missing, you could still try and kind of capture some aspects of the error that this then has in the model by using a stochastic approach. But I don't think you'd get as good a forecast as if then you tried to address those processes directly by building them into your model, of course. But I suppose this comes back to perhaps why SPPT has been so successful, is because it not only captures kind of our known unknowns, but also kind of unknown unknowns. So it captures a lot of uncertainty generally in the forecast from the limitations of the subgrid representation. So both from processes that you can't represent in a deterministic manner, but also from things that are currently missing in the model. And so I would hope that over time, as you improve the models, that ultimately you would be able to kind of scale down some of these perturbations. So of course, maybe as you include some other processes, you might recognize that they need to be represented probabilistically in their own right. So this is maybe one of the directions that we see stochastic parametrization moving, is that people are starting to go much more to a process basis and choose a particular process that needs addressing. And then you have this rather complicated situation of all these different uncertainties interacting with each other. Does that answer your question?
He says, yes, thank you.
Thank you.
Okay, well, I think we'll conclude here. Thank you again, Hannah, for a very nice talk, and I thoroughly enjoyed it myself. And thank you for everyone here participating and joining us in, and I encourage you to continue with this theme, which is present in some of the other sessions today, and to join us as well next week, where we have several other very interesting plenary lectures coming up. Thank you.
Thank you.